Hi, welcome to section 10.4, which is on symmetric figures. We're going to talk about symmetry, reflection symmetry and rotational symmetry for 2D figures, which are flat pictures like on a piece of paper, and then also reflection and rotational symmetry for 3D objects that we're also going to look at drawn on a sheet of paper, but just drawn in a three-dimensional way. And the first thing I want to do is I want to start and look at this picture is actually horrible. So I'm going to pull up a real picture of the Taj Mahal so you can see. Here are some good ones here. And this one, kind of like this one. This is a building that was created in India in 1630, and then in 1652 it was also built up a little bit more later, and it's completely symmetrical. And what that means, it has reflection symmetry and rotational symmetry. And by reflection symmetry, what I mean is that you could actually chop this building in half in multiple different ways, and the halves would be the same exact size and shape. So for example, like if you sliced it through the middle this way, or you could slice it through the middle this way, or you could even slice it on the diagonals, and it would create two halves that are exactly the same. And the cool thing about the Taj Mahal is the gardens are actually symmetric too. So the grass and the trees are symmetric. I think there's only a couple parts that are not. There's a couple of tombs located in the gardens, but other than that, everything is completely symmetrical, which is kind of cool. So back to the notes. Let's start with two-dimensional symmetry. So two-dimensional symmetry just means that, well, let's break it down. So the two-dimensional, again, just means that you've got something drawn on a flat sheet of paper. So the figure is flat. We're not talking about a real butterfly. We're talking about a picture, a flat picture of a butterfly or a flat picture of a sun. And then symmetry, it's symmetric if it can be folded in half and the two halves are equal. Or you could think of it as just being chopped in half and the two halves are equal. And the line where you fold or you chop is called the line of symmetry. And so it can have it's possible that a shape has one line of symmetry. It's possible that it has multiple lines of symmetry, and it's also possible that there aren't any lines of symmetry, that there's no symmetry at all. And so if you want, take a minute and pause the video and see if you can draw a line or maybe more than one line of symmetry on the shapes below. So the first thing that I'll look at this butterfly here. So I'll notice that I could draw a line, imagine that that's perfectly vertical, down the center, and the two halves are equal. So this butterfly is symmetric, and our line of symmetry is a vertical one down the middle. Now you can't, the reason that we wouldn't have a horizontal line of symmetry, if you can imagine for a minute, if you drew a line this way, if this top wing were to fold down on the bottom wing, it would actually be much bigger than the bottom wing. They're not the exact same size, so it does not have a line of symmetry horizontally. It only has one vertically. So I'll leave that one there. So one line of symmetry. This next one, this one's hard because it's a little small. This one would be easier to have if it was blown up a little bit and you could actually either cut it or fold it. But it looks like there's a line of symmetry there, and it looks like there's one here horizontally. And then it looks like we could also put one there, and then through each of the pieces in the sun. So it looks like we've got 4 lines of symmetry. So you've got one line, there's 2 lines, and there's 3 lines, and there's 4. I like to label them only because sometimes, especially when working with kids, I remember doing this with middle schoolers, a lot of times with ones like this, they would just count all of the parts of the line. So they'd say there's 1, 2, 3, 4, 5, 6, 7, 8, not realizing that they're counting the same line twice. So in this case, there'd be 4. This next one, it looks like there could be a line of symmetry down the middle. Not perfect, but it looks like it pretty good. And then this last one, it looks like there aren't any lines of symmetry. And part of it is because of this tilt here. If you were to even draw a line horizontally and fold this top half onto the bottom half, because this is on an angle, this part right here would come down to be right there and it wouldn't actually meet. And then if you try to draw a line this way, and fold it, the same thing would happen with these pieces here. Now the equal part, that would go ahead and it would meet the other half, the other side, but this top part would come down and it wouldn't meet the bottom part. So in this one, I'm going to say there are no lines of symmetry, so none. So what about shapes? So shapes we've talked about in the last couple lessons. So like squares, rectangles, equilateral triangles. Now in this chart, I'm going to attach and provide a sheet of paper with all of these shapes drawn on them. And what I would recommend is you cut each one of these out and fold them. So cut the square out and fold it in each different direction and try to see how many lines of symmetry there are. It's a little bit easier to visualize with a square, like we can just draw a square on our sheet of paper. And it looks like there's 1, 2, 3, and 4. So there are 4 lines of symmetry on a square. Rectangle, we could just do a quick sketch. And there's 1, 2 lines of symmetry on a rectangle. Equilateral triangle, we could even probably draw that one. So remember, this is a triangle with 3 equal sides, so they're the same length. So you could fold it this way, you could fold it this way, and you could fold it this way. And keep in mind, you know, my drawings aren't perfect. So again, it's a little harder to visualize when we're just sketching, but and then isosceles triangle, that would be a triangle where you've got 2 sides that are the same. And here we're looking at isosceles triangles that aren't equilateral, because it's possible an equilateral triangle is also considered isosceles. But I'm thinking of a triangle like this, where you could cut it in half this way, but that would be the only way that you could cut it in half. So this isosceles triangle has 1. And then what I would do if you've got that sheet, and I'll post that, you can pause the video and I would try and cut the rest out and see if you can figure those out on your own. And then I'm going to go ahead and just draw some quick sketches so we can visualize the rest of them. So for isosceles trapezoid is a trapezoid where the 2 non-parallel sides are the same length. So these are, we say, are congruent. And so isosceles triangle has 1 line of symmetry and it's vertical down the middle. So we've got 1. A trapezoid that's not isosceles. So there's a lot of different options there, but what I would do here is just draw, well, and you can use the one that's on the sheet, but if you think about a trapezoid that maybe looks like this, there aren't any lines of symmetry. So this would be none. And then a parallelogram, if we think about a parallelogram that's not a rectangle, something like this, there aren't any. It seems like there should be, but if you think about it, if you fold it this way, then this corner is not going to meet up. And then if you fold it horizontally, then this corner is not going to meet up with the bottom corner when you fold it down. So there's none here. And then we've got a regular dodecagon, and I'm going to go ahead and just use a picture for this one. So we can look at this regular dodecagon, and a dodecagon that's regular actually has, so it has 12 sides and there's 12 lines of symmetry. And the lines of symmetry are going to go, we've got 1 and then 2 and then 3 and then 4 and then 5 and then 6. And then there's a line of symmetry at all of the vertices. So we've got 1, 2, 3, 4, 5, 6. So if you connect each vertice to the one across, that's going to be a line of symmetry. And then between each vertice, if you draw a line between each vertice, then that's also a line of symmetry. And so if you actually draw each line, remember that when you're connecting one vertex to the other, that's considered one line. So even though there's 12 vertices, 2 as a pair are going to make 1 line of symmetry. So that's why there's 6 lines of symmetry going through the vertices, and then there's 6 lines of symmetry going through the sides. So there's 12 altogether. And there's no coincidence that it's a 12-sided figure and there's 12 lines of symmetry. So regular dodecagon is going to be 12. And it's very similar with the regular octagon. So I'll go ahead and draw that one real quick. So 1, 2, 3, 4, 5, 6, 7, 8. And so you've got a line of symmetry through each vertex. So we're going to go there, 1, 2, 3, and then 4. So that's 4. So 1, 2, 3, and 4. I'm labeling just so I don't count the bottom ones here twice, even though since they're connected and they're part of the same line. And then we're going to go through the sides. So 5, 6, 7, 8. So there's 8, and I'm just going to write, you might want to write 12 here, 12-sided figure for dodec again. And then a circle, if you think about a perfect circle, that's not a perfect circle, but imagine it is. A circle is going to have infinitely many, and I'm just going to draw the infinity sign. There's infinitely many ways that you can chop a circle in half as long as you're going through the center. If the line of symmetry is through the center, there's infinitely many ways that you can do it. And I know it doesn't seem like if you have this finite circle in front of you, like it would be infinity, but you know, even though through the naked eye, it doesn't look like you could fold it in a different way, there's always a way to shove another line in there. So for the regular pentagon, I'm just going to sketch that real quick. So it's a 5-sided figure. And regular means that the sides are all congruent. So imagine these are all the same length. And so you can, there's 5 vertices, 2, 3, 4, 5. And with this one, if you just draw a line of symmetry starting at each vertex, so there's 1, 2, 3, 4, and then 5, you don't have to draw additional lines between the vertices. You get 5 just doing it that way. So there's 5 lines of symmetry for a regular pentagon. And then last but not least, we've got a rhombus. So I'm going to come over here and just erase this. So a rhombus is a 4-sided figure where the opposite sides are parallel and all of the sides are the exact same length. And so there are 2 lines of symmetry for the rhombus. And I'll show you where those are. We've got 1 through those vertices on each corner, and then another line of symmetry through these vertices. And I'll just show you real quick. There's a better picture than the one I just drew, but you can see right here that's a little bit better, and an exactly drawn rhombus, and you can see those pretty clearly there. So that's about it in terms of reflection symmetry. Now let's talk about rotational symmetry. So rotational symmetry is when, if a figure has rotational symmetry, it means that if you turn it around, so imagine taking a shape, so any of these shapes here, so imagine taking like this rhombus and you set it on your sheet of paper and you rotate it, and you keep rotating it around a circle for 360 degrees, and if it ever makes the same exact shape than what it did when it started, then you know it has rotational symmetry. If you have to turn it around a full 360 for it to get back to its original shape, then it does not have rotational symmetry. So I'm going to show you just a quick video here that goes through whether or not this star has rotational symmetry. And so you'll notice before I hit play here that there's a little dot, a little blue dot at the top of the star. It's often helpful to mark the shape in some way so that you know where the top is. And that way when you turn it around, you can tell when you're back to the original shape. So I'm going to go ahead and just play this. So you can see there that this star has, it has rotational symmetry, and it rotates 5 times within 360 degrees. So we can actually figure out, if we want to, the number of degrees of rotation. And the way we would do that is we would take 360, the degrees in a circle, and we divide it by 5, and that would give us the number of degrees that it takes to turn the star and for the star to actually meet up and be the exact same shape. So let's go back to the notes. So you have a similar table for rotational symmetry than you did for reflection symmetry. And what I would encourage you to do is take the shapes, you should hopefully have these cut out, and what you would do, so for square, for instance, say you're going to take your piece of paper, your square that you cut out, lay it down on a sheet of paper, and then you're going to take, I'm going to use a different color to illustrate just tracing, and you're going to take a pencil and you're going to trace around your square. And then you're going to go and you're going to rotate that square a full 360 degrees and just note how many times it made the exact same shape, so where it fit. And you can draw a dot or a little arrow that shows this is where we start. So this is the starting place. So when you go ahead and rotate that square to the right, you know how many times you rotate before reaching back to the center. And I can show you, I'm just going to insert a square real quick here. Oh, not pictures. We want shapes and then rectangle, and I can just, you're not going to see the arrow, but you can get the idea. And then, so that this is the starting position, and I'm going to rotate, and now I'm meeting my original shape. So that's 1, 2, whoops, too fast, 3, and then back to the original, which is 4. So a square rotates, it has four times that it rotates throughout the 360 degrees. So in order to find the number of degrees, what we're going to do is we're going to take 360 and divide it by 4. So 360 divided by 4 is 90. So yes, and they're 90 degrees. And then we can do the same thing with a rectangle. So if we start out like this, then we can rotate. And when I rotate to the, whoops, to the right, oh, okay, so we're back. If I turn to, oh, maybe we're not back, I don't know. There we go. Okay, so if I start turning to the right, when I turn it 90 degrees, I don't make the original shape. Oh, and you know what? I forgot to trace it. Let me go ahead and trace it. That's a really important part. So I'm going to go ahead and trace the exterior. And it doesn't have to be perfect, but you get the idea. And then I'm going to turn. So, and you can turn in either direction. You can go right or left, counterclockwise or clockwise, just be consistent. So I'm going to start turning, and I'm going to turn, 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 turn. And if I turn, whoops, I missed that last one. So it looks like it's going to meet 1 time and then 2 times. So you always count the time that it meets itself. If there is rotational symmetry, then you count the time, the time where you have to rotate in order for it to be back to the original shape. So in this case, I rotated it twice, or there were 2 times that it made a mirror image of the original. So for rectangle, it's just going to be 360 degrees divided by 2, which is 180. So it's going to be 180 degrees of rotation. So I'm not going to go ahead and do the rest of these. What I'd like you to do is cut these out. Well, hopefully you have them cut out from before, and then go ahead and trace them and rotate them. And then I'm going to go ahead and fill out the answers, and you can pause the video and then check the answers when you're done. So for equilateral triangle, there are 3 vertices for equilateral triangle. It has 3, there are 3 times that it makes the same shape when you rotate. So 360 divided by 3 is going to be 120 degrees. Isosceles triangle, there are none. Isosceles trapezoid, there are none. Trapezoid that's not isosceles, we say none. A parallelogram, you can rotate it. It has there are 2 times that it makes the same shape. So 360 divided by 2 is 180. So if you rotate it 180 degrees, it's a mirror image of itself. A regular dodecagon, that's 12-sided. And again, regular means all the sides and the angles are the exact same. And so this one, if you rotate it, it actually rotates. There's 12 times it makes the same shape. So if you do 360 divided by 12, you end up getting 30. So every 30 degrees, there's a rotation and a mirror image. And then a regular octagon, that's an 8-sided polygon. For this one, it's going to be 360 divided by 8. So every 45 degrees. For a circle, there's infinitely many rotations because, as you can imagine, if you trace your paper circle, you can just rotate that however many degrees you want, and it's going to always look the exact same. And then a regular pentagon, which is a 5-sided figure, that's going to have 360 divided by 5 rotations, so 72 degrees each. And then a rhombus is going to be 360 divided by 2, or 180 degrees of rotation on that one. So let's just bump up real quick here. I just realized that I never did example 2. But with example 2, we've got some figures here, and it's going to be similar with the rotation. So for the top one, if you were to, imagine tracing this and then rotating it. So we trace it and we imagine this is up, and then we rotate it to the right. There's actually 3 different times that it makes the same image, and so there's going to be 360 degrees divided by 3, or 120 degrees of rotation. And then this figure, so we've got 1, 2, 3, 4, 5, 6, 7, so heptagon, a 7-sided polygon. There's going to be 360 divided by 7 degrees of rotation there. So 360 degrees divided by 7. I should have done this ahead of time. Forgot this one. 7 goes into 36 5 times. 5 times 7 is 35 with 10 left over. So it looks like it's 51 and some change with a little bit of remainder. So we'll just say about 51 degrees of rotation. And then with the snowflake, there's just like, you can kind of imagine that this is like a 1, 2, 3, 4, 5, 6-sided polygon, or a hexagon. There's going to be 6 times it rotates and meets itself. So 360 divided by 6, there's 60 degrees of rotation there. So now let's jump into the 3D figure. So this is harder because you really have to use your imagination. So if you think about this chair, and it might make more sense to think of a chair if there's one by you. Look at the chair, and I want you to imagine that you have a big machete, like a big knife that could slice through the chair. And I want you to imagine, if you were to stand up, is there any way that you could slice the chair so that the 2 halves would be the same? Now, it's harder to imagine halves being the same when it's 3-dimensional, but another way that you could look at it, and I put that here, by definition, it has reflection symmetry if each point on the left side has a matching point on the right, so that they are the same perpendicular distance from the plane of symmetry. So that's a mouthful. Let's talk about what that means. So imagine that you take a machete and you cut the chair directly vertical in half like that. Okay, so the points that I'm talking about, maybe the end, so these are labeled B and B complement. I know it's really hard to see, but these points, if you were to connect them with string, that string would form a right angle with this line of symmetry, or this plane of symmetry rather, because when you're cutting a 3-dimensional object, it's an entire plane. Like imagine, an entire piece of paper cutting through that. A up here matches this point right here. It looks like that's A prime. And again, if you were to take a piece of string and connect those 2 top parts of the chair, it would meet that plane of symmetry with a right angle. And so that's by definition, that's when we know that an object has reflection symmetry. So let's do a couple of examples. So do the following objects have reflection symmetry? So I know this is hard because we're not seeing these in real life, but imagine cutting this table. Now this is a table with a square top. I made sure to mention that so that we know it's a square. So you could chop it on the diagonals. So there's 1. You could chop it on this other diagonal, that's 2. You could chop it between the diagonals, so 3, and you could chop it this way, 4. And you have to pay close attention when you're chopping. You know, there's some legs down here as well, and so you have to think of the whole entire figure, not just the tabletop. And it looks like if we chop in those with those planes, that the legs would still be divided in exactly half, so that would work. This lamp, this is a little bit trickier to see. It's got 6 petals, and so it looks to me, and I would pause the video and think about these on your own first, but it looks to me like you could chop it between the petals. So there's 1, and I know it's hard to draw this, but there's 2, and then you could chop it again through that petal. And then it looks like I'll use a different color. You can see in between the petals, it looks like there's 4, 5, and then there's another one in the back that you can't see, 6. So I would say there's 6 for this one. And then last, this one, it has an octagon top, or it's octagonal. So it looks like, just like with the flat octagon, if we identify all of the vertices, we should have a plane of symmetry through each of the vertices. So we've got 1, we've got 2, we've got 3, and we've got 4, and then in between each one, so I'll use a different color, so 5, and then 6, and then 7, and then 8. So it looks to me like there's 8 there. And then with rotational symmetry, you almost have to imagine that you're standing, like for this table, for example, imagine that you're standing and you're flying in the air and you're looking down on the top of this table. And I want you to imagine taking your hands and rotating this table. So you're spinning it clockwise or counterclockwise. And imagine sort of tracing the legs and its shape on the floor, like the silhouette. As you're rotating this table, does it ever meet its original shape before you end up turning it a full 360 degrees? And I put here, you could almost imagine sticking a pole through the very center where you see this line L, and that's where you're going to sort of rotate it around, that invisible pole. And so this one, the top is a circle, so a circle has infinitely many ways you could rotate it. It always looks the same, but this, you've got to pay close attention. We've got 3 legs here, and so that's why there's 60 degrees of rotation here, because there's 3 of these legs. So if we divide the degrees in a circle, 360 by 3, we end up getting 60. So I pose a question here. Does any furniture in our classroom have rotational symmetry? Well, we're not in a classroom right now, but look around your home. Are there any objects, maybe the table, if you're sitting at a table, you know, if it's a table with a square top, usually those have rotational symmetry. Take a look at example 4. So do these objects have rotational symmetry? So this would be a great place to pause the video and try this on your own first. So with this glass pentagon floral container, so this top, imagine this is open, that's where your flower comes out, okay? And so let's say you are right here and you're looking down on this floral container, and you put your hands on the container and you start rotating it around. So it's sitting on the desk and you start spinning it around. How many times is it going to look exactly the same as when you started? Since it's a pentagon, and I'm guessing it's regular just by the shape, I know it's usually not good to just guess, but that's all we have here. It looks like there would be 360 divided by 5, so pentagon is 5-sided, that's why I'm dividing by 5, or 72 degrees of rotation there. The refrigerator, this one is tricky because the refrigerator is actually no. And the reason why it's no is because if, again, imagine that you're above this and you're looking down, the handle here is different. So if you were to rotate just a rectangle around. So if you're looking down on the top, if this is the top of your refrigerator, if it didn't have any handle, then it would have rotational symmetry. It would have it every 180 degrees because you could rotate this around 180 degrees and it'd look the same. But since we have this handle that's sticking out, when this gets rotated around to the bottom, the handle is going to be on the bottom and it's not going to match. With the laundry basket, this has handles evenly dispersed, so this would be a yes at 180 degrees. You could rotate that. The vase, since it's circular top, we'll assume it's circle. There's infinitely many ways that you could rotate that. And then with this vase, since there's a handle, I'm going to say no, because as you're looking down on it, you see the top of the vase, but then there's going to be a handle that's sticking out. And so as you rotate it, that handle is going to be in different positions. So that one's going to be a no. So I know that it's hard to look at this conceptually on a two-dimensional sheet of paper, but hopefully this helps. And again, I encourage you to really make sure you cut out those shapes that I'll attach for you, and then also just kind of look around your house and see if you can find some of these things and actually put your hands and rotate. And I think that'll make a lot more sense. And as always, if you have any questions, just let me know.